Welcome to the module on vibrations and aeroelasticity. In the last time in your dynamics module, you have looked at 3D dynamics, and in addition, you also looked at single degree of freedom system and touched upon 2 degree of freedom system. In this module, we will extend that and try to understand where to bring the concept of vibrations and how do we extend from single degree of freedom system and so on. But before we go there, let's try to do a quick recap, and let's also try to understand how what we are learning in this module is related to a lot of things that we would be learning later on, right? Or like, let's say, what we learned so far as well, right? So let's start with a quick recap and try to motivate why we are going to use some of the methods that we would be using in this module. Okay, so in previous lecture, let's say you looked at single degree of freedom system, and you looked at 2 degree of freedom system, right? So this was in your dynamics module in year 2, in your year 2 semester 2, right? For both of these, you probably looked at damped and undamped systems and undamped. Right? So essentially, what have we defined as vibrations? So, and we talked about this would lead to, we are looking at the module on vibrations, right? So what does it mean? We have some form of a moving object, and this object is moving about some mean, about a mean point, and it is moving in some periodic manner. Later in our damped, when we looked at damped system, you realize that this periodic manner, the period itself was changing, but at the end of the day, depending on the damping coefficient and so on, but at the end of the day, even that the amplitude is decreasing, but still the things are happening in a periodic manner, right? So that is kind of what we will be looking at. How are objects moving, and when they are moving about some mean point and in a periodic manner, and we are further interested when the shape of the object is changing, right? Shape of object is changing. So we said, as we said earlier, so let's say this was all the topics you learned in dynamics, and this was, let's say, all the topics you learned in structures, or in other words, this is often also called as elasticity. Then essentially what we are looking at is this intersection point. Let's say that's our dynamics or vibrations. Okay. So before we go into dig deep into it, let's try to recap some of the concepts. So if you remember, we had defined a simple spring mass system. So we had a spring, a mass, and a damper. So we said this is our mass, this is our spring, and then we have some kind of a damper. So we assume that the surface is frictionless. So what are the functions of each of these things? If I start, we will start slowly thinking from Newton's laws, where we are looking at force equilibrium, to thinking in terms of energy itself. So let's think of it if we think of it this in terms of energy, what is the energy stored or lost? Let's say, we can't say lost, but from each of these elements. We are itself saying that spring does not have any mass, damper does not have any mass in itself, but spring is defined by some kind of a spring coefficient, damper by some kind of a damping coefficient. right? So, but then the mass has inertia. So if you think about your first law of Newton's first law, the mass that is moving will have some inertia, and because of it, unless there's a force acting on this, the acceleration, or which means that the direction of motion or the speed at which it moves will not change, right? So mass has some inertia, or we can say it has some kinetic energy. Similarly, spring, when you pull it, it's some energy, you are doing some work on the spring, right? If I have to elongate something, I need to do some work on it, which means that this work is going to be stored in the spring, or known as the potential energy or spring potential energy. Lastly, damper. Let's say for example, let's say when you're in a cold weather, you'll probably say move your hand, or and you'll see that, okay, now I'm feeling much warmer, right? What is happening here? You're doing some work, and this work is being dissipated as thermal energy, or it's being going to heat up the surfaces. So there's some dissipation mechanism. So damper is giving us that dissipative effect. So there's a dissipation. Okay. So these are, let's say, our basic elements, our three more fundamental elements that we will be using again and again. Let's start with a very simple physical scenario, which you might have already done in the class. So let's say if you think of a physical scenario. So let's say we have some kind of a car. And this car is going on a very bumpy road. Okay. So this is our car, and we have a bumpy road. Which means this car is going to go up and down, right? And it's going to also go sideways, right? Front and back maybe as well a bit. But for all purposes, let's assume that the car only goes up and down, but not sideways or front and back and so on. In which case, what we have here is our physical system. And we need to convert this into some kind of a simple model, or mathematical model. So in other words, in this scenario, we probably, let's say we can think of some kind of a spring and some damper. And some kind of a mass. Okay. So now we can define, let's say this is moving along this x direction. So what are we interested in? We are interested in how this car is moving up and down. We have approximated the entire car by some mass. And then we are saying all these shock absorbers and all the systems are approximated by a spring and a damper. If I can understand how this mass is going to move up and down, or the system's response, so let's say whatever is being the bumpy road is nothing but our excitation force. So there is nothing but our excitation force. And whatever is x is nothing but our system response. So if one thing that we want to first think of is, what if just a bumpy road and kind of it leaves it, how will the car continue to move up and down? Nothing but our free vibration scenario. In this case, our mathematical equation tends to become mx dot plus c into x dot plus k into x equal to 0. Or we can have a scenario of forced vibration. How will the car behave as it continues to go on the surface? So this excitation force is continued to be applied. Then maybe I can say mx double dot plus c into x dot plus k into x equal to some f of t. And where, for example, here we know that our x dot is nothing but dx by dt, and our x double dot is equal to d square x by dt square. is nothing but our acceleration, and is nothing but our velocity. Okay, and f of t is nothing but our forcing function. We have approximated by some kind of a force to account for that bumpy road. Okay. Okay, so now we have some basic idea of what we want to do. So given any physical system, whatever this physical system is, we want to be able to convert that physical system into some mathematical model that we can easily play with. So now I can change the mass of the car, I can change the stiffness of the bumper, I can change the damping in the bumper and see, okay, if I change this, how will the system respond, or how will the car respond to that, all right? So that would give me an idea to design some of these systems. So now we can kind of look at it, slightly simplify even further as we did. So we can say case A or case 1, so we call it the undamped vibration. So what is the assumptions we are making here? One, that our damping is 0, no damping. Second, f of t is 0, no external forces. We'll try to see why we are doing it. We want to start with the most simplest scenario, in which case then for the above our mass would probably reduce it to something like, so you have a spring and you have a mass. This is our reduced system. Also the reduced equation would then be mx double dot plus kx equal to 0, or we can also write this as x double dot plus k by m into x equal to 0, and we call this as omega square, or we call this as natural frequency. Omega is our natural frequency, right? So this is what was done in the last year in dynamics, where you are given that this kind of what was the standard form, or we call this as a standard form. So if I can write an equation of motion and write it and bring it down to the standard form, using the equation I can directly extract the natural frequency. That is what we did last time. And also we set a general solution for this system, can be given to be x equal to a sine of omega n into t plus b cos of omega n into t. I'm not going to go into details of how we go in from the differential equation to a solution. It was briefly covered in your dynamics module, and also I've talked about some of the mathematics about this equation in the lecture notes that I have shared with you along with this. Also, where we also know that a and b are nothing but some constants. I can also rewrite this as, let's say if I write c is equal to I can also rewrite this as x equal to c into sine of omega n into t plus phi. So phi is nothing but what we called as a phase angle, and c is nothing but our maximum amplitude. Right? So we basically defined some kind of a wave, and we said if this is the wave, then we can say that this is nothing but our maximum amplitude. Okay, so this was all already covered in your dynamics module, but it's a good to just recap most of these things to get an idea and to understand what we have been doing. Next thing that we moved on was to say, okay, what if we have a damped system, right? So we had made one assumption, that our first assumption was c equal to 0, our original assumption. If we were to say this damping coefficient is not 0 but non-zero, then we want to consider that effect. In reality, this is always the case with any real system. For example, let's say if you have a pendulum and if it is moving, unless I'm going to apply a force or do some work, it'll stop. For example, let's say if I do this and you see it comes to a halt, because there's some maybe air resistance. Second thing, at the joint there is some friction between the pen and my hand, right? That acts as a dissipative effect in order to bring this pen down to a stop. So there's always some damping, some kind of frictional damping, viscous damping that exists. For example, it could be air resistance as well, right? So a simplest way to define damping is what's known as a fluid viscous damper, right? So let's assume for now let's assume C is not equal to 0 anymore, right? A simplest damper is what would be our fluid viscous damper, or what if it can define a damping force, nothing but C into X into dot. So it's nothing but a velocity. Similarly, just like how spring force is, let's say maybe we call it FD, just like how spring force is proportional to the extension of the spring, damper force is proportional to the velocity, right? So if so the question to think about, what would happen to the damping if there is sudden change in the velocity? Right? Just a question for you to go back and think about. So if we are going to say that there's some damping, that means that the oscillatory motion should come to rest, right? So in other words, we can say, let's say if our original system response, let's say X versus time, was a nice continuous sinusoidal. So this is, let's say, for the undamped. Then for the damped system, so that would be our damped system. And the equation of motion, right, which is in the standard form, I can write this as m into x double dot plus c into x dot plus k into x equal to 0. Okay. I will not going to derive these equations, but I think that has already been discussed in your dynamics module, and I would encourage you to go back and have a look at it. So one thing that we want to always think, okay, so if you remember, you said your solution would be something like x equal to e to the power of lambda t. That was what you said would be the solution. If our amplitude is the one that is decreasing every time, why can our solution not be, originally we had x equal to some c into sine of omega n into t plus phi, right? So this was our undamped. Why can't this be something by alpha into t? Okay, where alpha is some constant greater than 1. That means as time increases, our amplitude is being divided. The natural frequency continues to be the same, but only the amplitude gets divided, right? So it's a very simple question. What did we see here? We said here the amplitude is decreasing at every time instant, and after some certain amount of time. So basically, if it t tends to infinity, x tends to 0. Right? So the amplitude of vibration tends to 0. So if this amplitude is increasing, why can't we just divide by some alpha t? So just to think about it in a geometrical manner or a visual manner, let's try to plot out what would be some x equal to 1 over alpha t, or let's call it y just so that you're not confused. Let me plot y equal to 1 over alpha into t for t. Right? So if we are to plot this, you can see that the plot is something of this nature. That's our discontinuity. At time t equal to 0, the value of y is undefined, right? But then we need x to be defined all the way from time t equal to 0. Why? Because we need to calculate the velocity, we need to calculate the accelerations. So x is then, if x equal to, if x were to be c divided by alpha t into sine of omega n into t plus phi, that means x is undefined at time t equal to 0, which also means velocity x dot and acceleration x double dot are undefined. Okay. Since both of these are undefined, that makes it very hard for us to do any kind of calculation, because we don't know the derivative, we don't know the acceleration, we don't know the velocity, we don't even know the position. So how do we define how the system is going to move, right? So we said so that means that we need some function that can be differentiated continuously and infinitely, right? So it means we need a function that is continuous and differentiable. I'm not going to go into the details of this, but if you go back and look at the lecture notes, the typed out lecture notes, you'll see that I have gone into the mathematics of why exponential is a suitable function there. Okay, so that's the reason why we ended up saying we want to have e to power x minus lambda t is a potential solution. I'll leave it there instead of going and deriving these things, so that you can go back and read through the lecture notes, and I'm more than happy to elaborate or answer more questions as and when it arises. Okay, so going back to our equation of motion, so we have m into x double dot plus c into x dot plus k into x equal to 0. Or otherwise, I can also just write it, I can what we call as normalize with regard to the mass and say c by m into x dot plus k by m equal to 0. We already know from earlier that this is nothing but over omega square, which is the square root of natural frequency. Here we define another quantity called 2 into zeta into omega, where zeta is nothing but c divided by 2 square root of m into k. There's nothing but our damping ratio. we'll try to come back to understand what is the physical relevance of this damping ratio. But for now, let's assume that there's some kind of a quantity that we know, and we assume that this is useful to us. If I were to substitute, so now I have assumed that my solution is x equal to exponent of lambda t. Right. If I were to substitute this into my equation, right? So let's say substitute into the equation of motion. I get what we called as a characteristic equation. You have also used this in your when you did like second order quadratic equations, right? So when you did quadratic equations, you also had come across this characteristic equation. Which means I can have two solutions, lambda 1 comma 2, nothing but minus c over 2m plus or minus square root of c over 2m whole square minus k by. So we call critical damping coefficient or CC equal to 2m square root of k by m, or nothing but square 2m k. Sorry. So now if you go back to your damping ratio here, so our damping ratio is nothing but c divided by 2 square root of m into k, that is nothing but c divided by cc. So this is our critical damping coefficient, and this is our damping coefficient. It's kind of some kind of a ratio that says how close is your damping coefficient to the required critical damping coefficient of this system, right? So then we kind of also use these ideas to define three different cases. So we said three cases. One where the system is overdamped, one where the system is underdamped, and one where the system is critically damped. Okay. So here we are saying zeta equal to 1, underdamped it is less than 1, overdamped it is greater than 1. So if you go back and look at it, that is nothing but says that our damping coefficient is equal to the critical damping coefficient required for the system. That means it's critically damped. That means critically damped is just once the system starts oscillating, it comes to a rest and prevents any further oscillations. Underdamped is the system continues to oscillate for a much longer time, takes a lot of time to slow down. Overdamped system comes to rest very quickly, and for example, let's say if you suddenly hit a brake, its system could come to rest very quickly, but then at the end of the day, you are going to feel a jerk, or it's going to be uncomfortable in some extent, right? So in a way, overdamped systems are where the system comes to rest very quickly. Underdamped are where they take more time to come to rest as they continue to oscillate, and critically damped are systems which take just the right amount of time in order to come to rest. Next, we had talked about the concept of logarithmic decrement. Right. So if we take a system response of a damped system, so we said that So we said, let's say if this amplitude at this point x1 was at time t1. Similarly at time t2, let's say if the amplitude was x2, and again at time t3 the amplitude was x3, and so on. Then we can, what we want to understand is how fast is the system coming to rest. If we are going to understand how fast the system comes to rest, we want to know, let's say, what is the ratio of x1 to x2, right? Or we were more keen to understand the log of the ratio, and we define this as zeta into omega d into, omega n into tau d. This is what we call as a damped natural frequency, period of the damped vibration. Right? And then we use this idea of logarithmic measure to understand how fast the amplitude is reducing. These were all the concepts that we had covered in free vibrations, both free damped vibrations and undamped and damped vibrations. The next thing that we want to look at is what we did in our forced vibrations. Before we quickly introduce the topics in that, and then we'll lastly move on to look at one simple problem and see how we solve this problem using the Newtonian method, and how we can solve it in a more simpler way using the Lagrangian method. Right? So we talked quite a bit of, I have not introduced you to this Newtonian and Lagrangian yet, but we will come to that in a moment. So let's look at the forced vibrations before we go into it. So we talked about concept of forced vibrations. Essentially, let's say if we are going to think of a simple system, so let's again think of undamped vibrations here. So we have a spring, we have a mass, and additionally we have some kind of an external force, let's say F0 sine of omega t. So this is what we called as our forcing function. For example, in the example that we took, we had a car moving on a bumpy road. We said that the bumpy road is our forcing function, right? So what's our goal? Our goal is to determine the system response. Or nothing but x of t. So in the case of our undamped system, so our equation of motion can be written to be mx double dot plus k into x equal to F0 sine of omega into t. Or let's say omega naught. Let's call it omega naught just to differentiate from the omega n, which is nothing but our natural frequency. So what we did was we decomposed our solution x equal to some x into xc and xp. So we call this our complementary solution, and this is nothing but our particular solution. Okay. So complementary solution was nothing but what we discussed in our free vibrations. Or we can say xc is nothing but some c sine of omega n into t plus phi. And then we could probably also looked at some method where we solved that this particular solution is nothing but xp is some x sine of omega naught into t, where x was some amplitude. And we defined our overall solution, so we can write that overall solution. And for example, we also said that if you substitute this and we are able to get x there, we could write our xp finally as some f0 divided by k 1 minus omega naught by omega n whole square sine of omega naught into t, which means our total system response became nothing but x is nothing but c sine of omega n into t plus phi. I'm not doing anything much here. I'm just adding both the terms and writing them just in one single line. But we will see why that in a moment. Sine of omega naught into t. So as the forcing function continues to be applied, we can say initially our complementary solution is only transient. As the forcing function continues to be applied, let's say till infinity, the solution stabilizes to our particular component, right? Initially there's some transient effect because the forcing function, there's maybe the lag between the forcing function and the system response. So initially we have a transient solution, and finally we have a stable state, that either goes with the forcing function or with some phase difference with the forcing function, right? So there's nothing but our transient phase, and there's nothing but our steady state solution. Okay. So then we said, okay, what we looked at some concept. We'll now look at some concept called magnification factor. Right? How much is the amplitude being magnified as the frequency increases? So we know that as the frequency reaches the natural frequency, our amplitude of vibration increases to infinity. Right? So if we were to plot our magnification factor, so we said a magnification factor. So let's say MF is nothing but the amplitude of vibration divided by F naught by K, or we said this is nothing but 1 minus omega naught by omega n whole square. So if I were to plot this, right? So my magnification factor, let's say it starts from 1. So this is nothing but omega naught over omega n, right? Sorry, this is our axis, and this is the value of 1. Right? So then I can say my magnification factor so it has some profile like this, which means as the amplitude of our forcing function reaches the natural frequency, or what we called as a resonance, right? So this was nothing but our point of resonance. The amplitude of vibration increases to infinity, which means the magnification factor increases to infinity. So this was a quick recap of what you have studied so far in free vibrations and forced vibrations, damped and undamped systems. What does the equation of motion look like? What does the solution look like? Just to give you an idea of where we stand. In the next state, we will try to look at a very simple problem for a 2 degree of freedom system. This is something that you have already done. And recap how we solved this. The reason for looking back is we want to understand why we are going to use the Lagrangian method. And in order to do that, we need to just recap what we have done so far. Okay, so let's consider this very simple system. We have 2 masses and 3 springs connected. So we have a mass M1 and M2. These are connected to the top and bottom and in the middle by 3 springs with spring constants K1, K2 and K3. What is our goal? We want to understand how the mass M1 is moving. So we have defined the direction as x1. And the amount it would move as x1. Similarly, for the mass m2, we defined that it is moving by some amount x2. Okay. So we have 2 ways to solve this problem. One is the Newtonian method, and one is what's called as a Lagrangian. So far in your earlier dynamics module, you used the Newtonian method. So what did you do? You said summation of F is equal to some m into acceleration, right? Or some summation of m, which is your moment of inertia. Moment is nothing but I, moment of inertia, into some theta double dot or angular acceleration. So you calculated for each of these mass, you calculated what is the force acting on it. So if you take each of these mass, there's one force acting on the top because of the spring, one force acting on the bottom because of the spring, right? And same thing with your second mass as well. Of course, we can consider the mg, which is the gravity load, but this will get cancelled out. So for now, we can neglect that at this point. Okay, and that means that here it's easy because it's moving in one direction. What if I put an additional spring here and allow the spring, this one, to also move in this particular direction? For now, we will not do that, but just to think of different things that could happen to this mass, it need not necessarily be always moving in a single direction, which means you'll need to consider the forces in all these directions, x direction, y direction, also do all the components and sum them up, right? So then in that case, this could become fx equal to ax and summation of fy equal to m into ay and so on and so forth. Same thing with the z direction. Lagrangian is slightly a different take. It looks at what is the total energy in the system, right? So in a way, we are looking at what is the energy, right? What is the kinetic energy, potential energy. In other words, here we have vectorial quantities, and here we have a scalar quantity. Many of you might already be feeling relieved because it's not vector, it's a nice scalar. There's one number in there. There's no direction to that number, right? So if you can define the kinetic energy, if you can define the potential energy of each of the components in the system, then you can use what's called the Euler-Lagrange equations to solve this. Okay. So you already done in the Newtonian method. What did you do? Let's say you took the equation of motion for mass 1. So let's say we start with the Newtonian method, right? So you wrote the free body diagram. First step was to write the free body diagram. So you took mass m1. I said there's a spring force acting on top, x1. I said the spring force acting on bottom. I'm going to just write it as x1 minus x2. Why is this the case? The top spring is pulled in some amount x1, but the bottom spring, bottom spring is also pulled by the mass m1 and by the mass m2. So m2 is moving by x2, m1 is moving by x1. So the relative displacement is x1 minus x2. That is the elongation of the spring in the K2 spring, right? Similarly, I need to write the free body diagram for m2. I'll have again say K2 into x1 minus x2, and I'll have K3 into x2, right? So our second step is to take this, and so we can define that m1 is moving in this direction with m1 x1 double dot, moving in this direction with m2 x2 double dot, right? So we can write the equilibrium equation of motion for both masses. So that would be m1 x1 double dot plus, is equal to minus k1 x1 minus k2 into x1 minus x2 plus f1 of t. So let's also, if we were to say we apply some kind of a forcing function, right? Similarly for mass 2, so we can write m2 into x2 double dot is equal to minus k2 into x1 minus x2 minus k3 into x2. Or if I want to rearrange this, I can rearrange this in some kind of a matrix form. x1 double dot x2 double dot plus k1 plus k2 minus k2 minus k2 k2 plus k3 x1 and x2 is nothing but f1 of t 0. Or I can also write it in a more simpler form, saying m into x double dot plus k into x equal to f. Right? That looks like our standard equation of motion, but in a matrix form. Right? This means that we had to first write our free body diagram. In order to write our free body diagram, we need to know what forces are acting on the system. What directions are these forces acting? Here it's very simple because we have a simple scenario where it's going in one direction, but as in more complex scenarios, you might have things moving in different directions, force coming in from different directions. Right? This is kind of where the Euler-Lagrange equations come in very handy. Right? So we can define our kinetic energy. We can define our potential energy. And we can also define some kind of a dissipation. And since the friction here there's no friction, and we are assuming undamped system, we can easily say that let's say the dissipation is 0. Right? So where is the kinetic energy coming from? We already discussed when we started our class. Let's go back to the very first slide. So when we started our class, we said that spring stores some potential energy. Mass has some inertia, so there's some kinetic energy in the mass. Right? So we already discussed these things, and we said the damper has some dissipation. We said now we don't have a damper, so there's no dissipation. So kinetic energy is coming purely from the mass. So we have two masses that are moving, one in x1 direction, one in x2 direction, and with accelerations x1 double dot and x2 double dot. So knowing this information is sufficient to write half m1 into x1 double dot plus half m2 into x2 double dot. Similarly, our kinetic energy our potential energy is because of the spring elongation. So we have three springs, x1 square plus half k2 into x1 minus x2 square plus half k3 into x3 square. We didn't look at the directions or anything here. We know that each of these elements stores a certain type of energy. Mass stores inertia, so there's kinetic energy. Spring stores some potential energy because of spring elongation. We use this idea to directly write it. It has nothing to do with the free body diagram itself. Now, I will not going to talk about how I got this magic equation. We'll do that in the next two classes, but for now we assume that I am giving you the right equation. Right? So we have something called the Euler-Lagrange equation. Right? So this can be written as d by dt of dt by dx dot minus dou t by, sorry, this has to be dou by dou into x minus dou into v or dou into x plus dou into d or dou x dot equal to q. So this is our equation. So T is nothing but our kinetic energy, V is nothing but our potential energy, total of the system, D is nothing but the total dissipation in the system. Okay. And Q is nothing but any external forces that are acting. Here our forcing function. We can use this equation to calculate for both the masses. Let's say we do for mass 1. So we can say d by dt of dou t by dou x dot. Why dou here? Because t could be defined on both x and time. Right? So if I take my kinetic energy and divide by x dot, right? So then essentially I'm going to end up with x1 dot. I don't have any relation with regard to x1, so this goes to 0. We'll go in detail look at it in a moment, but for now, just to quickly see how quick we can get our equation of motion. Plus, if I'm going to do the derivative with regard to for the spring energy, I can write k1 x1 plus k2 to x2 minus x1 or x1 minus x2 plus 0 equal to f1 of t. Or in other words, I have m1 x1 double dot, right? Sorry, so I made a mistake here. So the kinetic energy should be half m into x1 dot square plus half m2 into x2 dot square, right? Plus k1 x1 plus k2 to x2 minus x1 minus x2 equal to f1 of t. Similarly, you can do the same thing for mass too. I'll leave it to you to do. And if you put it back into a matrix form, you'll realize that you're getting exactly the same equation that we got from the Newtonian method. Of course, it's probably a little harder to see the actual advantage here, but one thing that is very obvious, you did not have to write a free body diagram itself. All you needed to know is what are the masses in the system, how fast are they moving, what are the springs in the system, how are they getting elongated, what is the net elongation of this spring, not the direction, just the net. These are all scalar quantities, the kinetic energy, potential energy, and you use that to get your equation of motion. And you get the same equation of motion as in your Newtonian method. So let us call it a day here. In the next class, we'll try to see how we arrived at this Euler-Lagrange equation, how can we use it, and we'll look at more complicated problems where it might be much more harder to solve using the standard Newtonian method. Thank you very much and have a nice rest of the week, and see you next Monday.